Good evening, students. This is Arvind, Asst.Professor, Department of Triple DBSIT Kavali. So, in the previous sessions, I discussed about harmonics concept of alternator, and now I'm going to discuss different, that is, the effects of harmonics on different factors, that is, winding factor, pitch factor, and distribution factor, and induced EMF of an alternator. Okay. So, firstly, I will discuss effect of harmonic components on induced EMF. So here the flux density distribution, okay, the flux density distribution around the air gap in all alternators is symmetrical with respect to abscissa. Abscissa means the distance between the point from vertical y-axis and parallel to the x-axis, that is abscissa. Okay, the flux density distribution around the air gap in all alternators is symmetrical with respect to abscissa and also to polar axis. Okay, it can be expressed with the help of Fourier series which do not contain even harmonics. Okay, it can be expressed with the help of Fourier series which do not contain even harmonics. Okay, next, here the flux density at an angle theta from the interpolar axis is, so flux density B is equal to Bm1 into sine theta plus Bm3 sine 3 theta plus and so on plus Bmx sine x theta. This is the flux density at an angle theta from the interpolar axis. So it is indicated as a equation number 1. So where x is order of harmonic which is odd, order of harmonic which is odd, that is 1 3 5 7 9 like this, and Bm1 is the amplitude of fundamental component of flux density, and Bmx is the amplitude of x harmonic component of flux density. Okay, and next we have the EMF generated in a conductor on the armature of a rotating machine is EC is equal to BLV sin theta. This is, you already know, EC is equal to BLV sin theta. So here theta is equal to 90 degrees. Then EC is equal to BLV. That is the EMF generated in a conductor. EC is equal to BLV because sin 90 is 1. From the trigonometrical functions, sine 90 is equal to 1. That's why I am writing EC is equal to BLV and substituting the value of B in equation 1. That is, in the previous case, I am writing B is equal to BM1 sine theta plus BM3 sine theta plus and so on BMX sine theta. So I am substituting that one into this one. That is, EC is equal to Bm1 sine theta plus Bm3 sine 3 theta plus and so on Bmx sine x theta into Lv. This is treated as second equation. So here L is equal to length of the conductor and d is diameter of the armature and v is linear velocity. So actually linear velocity formula is pi into d into ns. So here ns is the 2f by p, and from this one I am writing v is equal to pi into d into 2f by p. That is the linear velocity. V is equal to pi into d into 2f by p. So and next, substitute the value of v in equation 2. We get EC is equal to the B equation is same, that is Bm1 sin theta plus Bm3 sin 3 theta plus Bmx plus and so on plus Bmx into sin x theta into L. In V place I am substituting 2 pi df by p, that is the linear velocity, 2 into pi into df by p. So from this one I am writing EC is equal to Bm1 into pi dl by p into 2f into sin theta. Okay, Bm1 into pi dl into 2f sin theta plus Bm3 into pi dl by p into 2f sin 3 theta plus and so on plus Bmx into pi dl by p into 2f sin x theta. Okay, after substituting the v value, we will get this one. And then the area of each fundamental pole is, that is A1 is equal to pi dl by p. That's why I am substituting in A1 place pi dl by p. So from this one I am writing EC is equal to Bm1 into in pi dl by f, pi dl by p place I am substituting A1 value, that is Bm1 into A1 2f sin theta plus Bm3 into A3 2f sin 3 theta plus and so on plus Bmx into Ax 2 sin x theta. Okay, and area of x the harmonic pole, that is Ax is equal to, from the area of each fundamental pole I am writing x the harmonic pole, Ax is equal to pi dl by xp. So that is equal to, you know that pi dl by p is equal to a1. Substitute here, we will have a1 by x. Okay, so from this one I am writing a1 is equal to x into ax, x into ax, and then ec is equal to 2f into bm1. So here I am taking the ef as common factor, that is ef of bm1 a1 sin theta plus bm3 into 3 into a3 sin 3 theta plus and so on, plus bmx into x into ax into sin x theta. So from these I am writing ec is equal to 2f of you know that phi m1 is equal to bm1 into a1. Here substituting in place of bm1 a1 phi m1. So we will have phi m1 into sin theta plus 3 into phi m3 into sin 3 theta plus and so on, plus x into phi mx into ax into sin x theta. Okay. So where phi m1 is equal to bm1 a1, this is the maximum value of fundamental flux per pole. Okay, so from this one I am writing phi 1 is equal to 2 into phi m1 by pi. So that is the average value of fundamental flux per pole. This is the average value of fundamental flux per pole. Similarly, average value of x the harmonic is phi x is equal to 2 into phi mx by pi. So that is equal to 2 by pi into bmx into ax. And substitute in the values of flux in EC, we get EC is equal to phi f of phi 1 sin theta plus 3 into phi 3 sin 3 theta plus and so on, plus x into phi x into sin x theta. So the instantaneous value of fundamental frequency EMF generated in a conductor is EC1 is equal to phi f into phi 1 sin theta. This is the instantaneous value of fundamental frequency EMF generated in a conductor. From the above equation I am writing this one, and then the RMS value of fundamental frequency EMF generated in a conductor EC1 is equal to pi into f into phi 1 by root 2. This is the RMS value of fundamental frequency EMF generated in a conductor. So from this one I am writing pi by root 2 value, we have 2.22 f into phi 1. This is the RMS value of fundamental frequency generated in a conductor, frequency EMF generated in a conductor. And next I am writing the RMS value of x the harmonic frequency EMF generated in a conductor is E suffix Cx is equal to 2.22 f into phi x. So here phi x is equal to 2 by pi into bmx into ax. Okay, substitute this equation to this one. So we will have ECx is equal to 2.22 into, in phi x place I am substituting 2 by pi bmx into ax into f. Okay, from this one I am writing phi x is equal to 2 by pi into bmx into a1 by x1, and substitute here, that is ECx is equal to 2.22 into 2 into a1 into bmx f by x pi. Okay, so while substituting this one we will get this one, and from this one I am writing 4.44 into a1 bmx into f by x pi, or we will write 4.44 ax into bmx into f by pi. So this is the RMS value of x the harmonic frequency EMF generated in a conductor. And from this one I am writing ECX is equal to 1.4132 into A1 into BMX into F. Okay, from this one I am writing 1.4132 into A1 into BM1 into F. That is the fundamental RMS value of fundamental harmonic frequency EMF generated in a conductor, that is EC1, and RMS value of x the harmonic frequency EMF generated in a conductor is ECX. So from these two I am writing ECX by EC1, that is equal to 1.4132 A1 into BMX F by 1.4132 A1 into BM1F, that is equal to, we will write BMX by BM1. Okay, so from this one we will have ECX by EC1 is equal to BMX by BM1. So from this one I am writing ECX is equal to EC1 into BMX by BC1. So from this one I am writing RMS value, that is EC is equal to root of EC1 square plus EC3 square plus and so on ECX whole square. This is the RMS value of EC. That is the frequency EMF generated in a conductor. Okay. And next we will have effect of harmonics on Kp, that is the pitch factor or coil span factor. Okay, effect of harmonics on Kp. So for that one I am writing let alpha is equal to angle of short pitch. This is alpha, that is the angle of short pitch, that is the fundamental component, and 3 alpha, that is the third harmonic component, and 5 alpha, that is the fifth harmonic component, and x alpha, that is the xth harmonic component. So from this one I am writing Kpx, that is equal to cos x alpha by 2. You know the formula for the pitch factor, that is Kp is equal to cos alpha by 2. So from this one I am writing for the x harmonic component, pitch factor Kpx is equal to cos x alpha by 2. Okay, and next I am writing distribution factor. There is the effect of harmonics on distribution factor. You know the formula for the distribution factor, Kd is equal to sine m beta by 2 by m sine beta by 2. Similar to the pitch factor, distribution factor also different for various harmonic components. So for that one, for the x harmonic, we will write distribution factor as Kdx is equal to sine x m beta by 2 by m sine x beta by 2. So if we take x is equal to 1, then Kd1 is equal to sine m beta by 2 by m sine beta by 2, that is for the fundamental component. And next for the third harmonic component we have Kd3 is equal to sine 3 m beta by 2 by m sine 3 beta by 2. This is for third harmonic component. And next total EMF generated due to harmonic component. So you know the formula for the induced EMF per phase. For the alternator, even phase is equal to 4.44 into Kp1 into Kd1 into phi1 into F into T phase. Whereas here T phase is the turns per phase and Kp1 is the pitch factor for the fundamental component, and Kd1 is the distribution factor for fundamental component, and phi1 is the fundamental component flux value, and F is the frequency. Okay, so for x harmonic component, Ex per phase is equal to 4.44 into Kpx into Kdx into phi x into F into T phase volts. So from these two we will have total phase EMF, that is E phase is equal to root of E1 phase whole square plus E3 phase whole square plus and so on plus Ex phase whole square. This is the total phase EMF. And next we have effect of harmonics on line EMF. So actually for star connection, the line voltage is root 3 times the phase voltage. You know already this one. So for star connection, the line voltage is root 3 times the phase voltage. So for that one I am writing EL is equal to root 3 into E phase. So here EL is the line voltage and E phase is the phase voltage. For a star connection we have root 3 into E phase. Okay, but it should be noted that with star connection, the third harmonic voltages do not appear across line terminals through present in phase voltages. So actually in delta connections, also third, ninth and fifth harmonics do not appear at the terminals. Okay, that means E line is equal to root 3 into root of E1 phase whole square plus E3 phase whole square plus and so on EX phase whole square. This is the line EMF or line voltage. Okay, and from this one I am writing E1 phase by EX phase, that is equal to 4.44 into Kc1 into Kd1 into phi1 into F into T phase by EX phase, that is 4.44 into Kcx into Kdx into phi x into X F T phase. Okay, from this one I am writing E1 phase by EX phase, that is equal to Kc1 into Kd1 into phi1 by x into Kcx into Kdx into phi x. Note the point, the important point is if third harmonic is given to be 10% of fundamental, then phi 3 is equal to 1 by 3 of 10% of the fundamental. So this is for third harmonic. Is given to be 10% of fundamental, then phi 3 is equal to 1 by 3 into 10% of the fundamental. Okay, we will see some numerical problems on effect of harmonics. Okay, so in those, first problem is an alternator has 18 slots per pole and first coil lies in slots, that is 1 and 16. In between 1 and 16 the first coil lies, and calculate the pitch factor for fundamental harmonic and third harmonic and fifth harmonic and seventh harmonic. So we have to calculate the pitch factor for fundamental harmonic, third harmonic, fifth harmonic, and seventh harmonic. So solution for this problem is, firstly we will take the data, given data, that is number of slots per pole. They given that n is equal to 18 and first coil lies between slots 1 and 16. So for that one we will find pitch factor for fundamental harmonic, third harmonic, fifth harmonic, and seventh harmonic. And then we know that pitch factor Kp is equal to cos alpha by 2. So, and we also know that beta is equal to 180 by n. In the problem they already given that number of slots per pole, that is 18. Substitute that value into this one, so we will have beta is equal to 180 by 18. From this one we will get beta value as 10 degrees. And number of slots short pitched is, we will have already number of slots per pole 18, and the coil lies between 1 and 16 slots, that means 16 minus 1. So that's why we will have 15, and number of slots short pitched is 18 minus 15, that is equal to 3. Here 18 is the number of slots per pole minus 15 is the number of slots short pitched, that is for the given problem, for the problem they given that the coil is lies between 1 and 16 slots. From that one I am taking 16 minus 1, we will have 15. So here number of slots short pitched is equal to 18 minus 15, that is equal to 3. So we know that alpha is equal to, you know the formula for alpha, that is equal to beta into number of slots short pitched. So here the number of short pitched is equal to 3. So substitute that value into this one. So alpha is equal to beta into 3. So previously we calculated beta value. So we will have 10, substitute here. So alpha is equal to 10 into 3. We have 30 degrees. Alpha is 30 degrees. So by using these values, we have to calculate the fundamental pitch factor for fundamental component and third harmonic component, fifth harmonic component, seventh harmonic component. Firstly, we will see the pitch factor for the fundamental component. You know the formula, effect of harmonics on the pitch factor, that is cos x alpha by 2. Here we will take the fundamental component, that is x value is 1. Here x is equal to 1. Substitute here cos into 1 into alpha by 2, that is cos 30 by 2, that is equal to cos 15. From the trigonometric functions we have cos 15 is equal to 0.965. And coming to the second case, that is third harmonic component, we know the formula for the third harmonic component for the pitch factor, that is cos x alpha by 2. Here x is equal to 3. So cos 3 alpha by 2, that is equal to cos 90 by 2, that is equal to cos 45. From the trigonometric functions we have 0.707. And next, fifth harmonic component, for the pitch factor for the fifth harmonic component, we know the formula cos x alpha by 2. Here x is equal to 5. Substitute here, we will have cos 5 alpha by 2. So that is equal to cos 150 by 2. That is equal to cos 75. That is equal to 0.258. And next, coming to the fourth case, for the seventh harmonic component, we know the formula cos x alpha by 2. So here x value is 7. Substitute here, we have cos 7 alpha by 2, that is equal to cos 7 into alpha value is 30, that is cos 210 by 2, that is equal to cos 105, that is equal to minus 0.25. These are the different pitch factors for the different harmonic components, that is fundamental component, third harmonic component, fifth harmonic component, and seventh harmonic component. Okay, this is the solution for the given problem. And next, coming to the second problem, here calculate the RMS value of induced EMF per phase of a 4-pole 3-phase 50 Hz alternator with 3 slots per pole per phase and 6 conductors per slot in 2 layers. Here the coil span is 150 degrees. The flux per pole is a fundamental component of 0.2 Webers, and 16% third harmonic component. So from this data, we have to calculate the RMS value of induced EMF per phase. Okay, so firstly we will take the solution by taking the given data, that is in the problem they given that m value, that is number of slots per pole per phase, they given that the value is 3. From that one I am writing m is equal to 3, and they given that number of poles p is equal to 4, and frequency they given that 50 hertz, and they given the coil span is 150 degrees, and flux value they given, that is flux per pole 5 1 is equal to 0.2 Webers. The two fundamental component. Here the fundamental value is 1. That's why I'm taking the flux value 5 1 is equal to 0.2 Webers. So from this one we have to calculate the RMS value of induced EMF per phase. So for that one we have to calculate some more parameters, that is you know the formula, number of slots per pole per phase, m is equal to n by 3. Here it is a 3-phase alternator, that's why m is equal to n by 3. That is number of phases. So you know already m is equal to 3 value. Substitute here 3 is equal to n by 3. So from this one we will calculate n is equal to 9. There is a number of slots per pole, n is equal to 9. We calculated from the m value, given m value, that is number of slots per pole per phase. And next we know that n is equal to number of slots per pole, and here we calculated n value, that is 9, that is equal to number of slots by 4. So here from this one I am calculating number of slots per pole, that is equal to 36. That is equal to 36. So by using this formula, this value, we have to calculate the total number of conductors, but in the problem they given that number of conductors per slot also. By using those we will calculate the Z value, that is Z is equal to number of slots into number of conductors per slot. Okay, here number of slots is 36, and number of slots per slot, number of conductors per slot, they given that 6. So here in the problem they given that what they given, the alternator has 3 slots per pole per phase and 6 conductors per slot in 2 layers. So from this one I am writing Z is equal to number of slots, that is 36, into number of conductors per slot, that is 6. So totally we have Z is equal to 36 into 6, we have 216, and Z phase, that is a total number of conductors per phase. So here 3 phase value we have, that's why per phase we have to calculate the number of conductors, that is 216 by 3, that is equal to 72. So from this one I am calculating turns per phase also. You know the formula for the Z phase, that is equal to 2 into turns per phase, turns TURNS. So from that one I am writing turns per phase is equal to Z phase by 2. So that is equal to Z phase value is 72 by 2, that is equal to 36. Okay, you know the coil span factor, that is equal to 150. Actually we know that coil span factor is 180 minus alpha. So that is 180 minus alpha is equal to 150. From this one we have alpha is equal to 30 degrees, and you know the formula for the beta, that is equal to 180 by n. You know the n value is 9, that is 180 by 9, that is equal to 20 degrees we have. Okay, that is beta value is 20 degrees, and then you know the formula for the pitch factor, that is Kc1 is equal to cos alpha by 2. This is for the fundamental component, that is Kc1 is equal to cos x alpha by 2. Here x value is 1, that is the fundamental component, that is a cos 1 into alpha by 2, that is equal to, you already have the alpha value, that is 30 degrees. Substitute here, we have cos 30 by 2, that is equal to cos 15. From the trigonometric functions we have cos 15 is equal to 0.965, and similarly distribution factor for the fundamental component, that is KD1 is equal to sin m beta by 2 by m sin beta by 2. So here x is equal to 1. Substitute here sin m beta by 2 by m sin beta by 2. Here m value is 3. Substitute here, and beta value is 20. Substitute here. We have sin 3 into 20 by 2 by 3 into sin 20 by 2. That is equal to sin 30 by 3 sin 10. So KD1 is equal to 0.959. And next we have to calculate the EMF value per phase, that is E1 per phase is equal to, you know the formula, that is 4.44 into Kc1 into Kd1 into phi1 into F into T phase. So from this one we are writing, this is for the fundamental component. Okay, so that is 4.44 into Kc1 value is 0.965 into Kd1 value is 0.959 into flux value is 0.2 into 36. You have the EMF formula, that is even phase, that is equal to 1479.2 volts. That is for the first fundamental component, and for third harmonic Kc3 is equal to, that is Kcx is equal to cos x alpha by 2. Here x value is 3. From that one, Kc3 is equal to cos 3 alpha by 2. You know the alpha value, that is 30, and cos 3 into 30 by 2, that is equal to cos 45, that is equal to 0.707. And next we have to calculate the KD3, that is the distribution factor value, that is KD3 is equal to sine 3 m beta by 2 by m sine 3 beta by 2. So that is equal to sine 3 into m value is 3 into beta value is 20 by 2 by m value is 3 into sine 3 into beta value is 20 by 2. So KD3 is equal to 0.666. Okay. And next we know that flux harmonic component of x, the harmonic component of flux value is phi x is equal to 1 by x into phi 1. So for the third harmonic we have the flux value, that is phi 3 is equal to, in the problem they given that 1 by third of the 16% of flux for the fundamental flux. That's why I am taking x value as 3, that is phi 3 is equal to 1 by 3 into 16% of phi 1. Okay, you know the phi 1 value, that is 0.2. In the problem they given that flux is fundamental component flux value is 0.2 weber's. So here, and also in this one they given that 1 by 16th 16% of third harmonic component they given. So for that one I am writing, so 16% of 500 is 0.010 weber's. Okay, so E3 per phase, that is the third harmonic component EMF value, that is E3 per phase is equal to 4.44 into Kc3 into Kd3 into phi 3 into 3 into F into turns per phase. So that is equal to 4.44 into Kc3 value is 0.707 and Kd3 value is 0.666 into third harmonic component flux value is 0.010 into 3 into flux value frequency value is 50 into 36, transfer phase is 36. By solving this we have 112.89 volts, that is the EMF value for the third harmonic component. And next, RMS value of induced EMF for the problem is ERMS is equal to root of even phase whole square by E3 phase whole square, that is equal to root of even phase value is 1479.2 whole square plus E3 per phase value is 112.89 whole square. Totally we have ERMS value is equal to 1483.3 volts. This is the solution for the second problem. Okay, and coming to the third problem. So here the phase EMF of three-phase alternator consists of fundamental 20%, third harmonic, and 10% fifth harmonic. Okay, the amplitude of fundamental is 1000 volts. Calculate RMS values of line and phase voltage. So when the alternator is connected in star and delta connections. Okay, for that one we have to calculate the RMS value of line and phase voltage when the alternator is connected to star and delta connection. So from the problem, I am taking the given data, that is even phase, that is equal to 1000 volts. That is the amplitude of fundamental is 1000 volts, that is even phase, and E3 phase is 20% of fundamental, that is 0.2 into 1000, that is equal to 200 volts, and fifth harmonic 10%, that is E5 phase is equal to 10% of fundamental, that is equal to 0.1 into fundamental value is 1000, that is equal to 100 volts. Okay. And next we have RMS value of induced EMF, that is even phase RMS, that is equal to even phase by root 2. So that is equal to, we have the even phase value, that is 1000 by root 2, that is equal to 707.11 volts, and E3 phase E3 phase RMS value is equal to E3 phase by root 2, that is equal to 200 by root 2. We have 141.42 volts, and E5 phase RMS, that is equal to E5 phase by root 2, that is equal to 100 by root 2. That is E5 phase RMS value is 100 by root 2. Sorry, E5 phase value is 100 by root 2, that is equal to 70.71 volts. And for the star connection, we have E phase is equal to root of E1 phase whole square plus E3 phase whole square plus E5 phase whole square. So you know the value for E1 phase, that is 707.11 whole square plus E3 phase, that is 141.42 whole square plus 70.71 whole square, that is E5 phase whole square value. That is equal, total we have E phase value is for the star connection 724.56 volts. And next we have for the star connection, line voltage is equal to root 3 into root of E1 phase whole square plus E5 phase whole square. So from the data we have root 3 into root of E1 phase value is 707.11 whole square plus E5 phase value is 70.71 whole square. Totally we have line voltage for the star connection is 1230 volts. And similarly for the delta connection, you know already the line voltage is equal to phase voltage, so that is equal to root of E1 phase whole square plus E5 phase whole square. So substitute E1 phase value and E5 phase value here. So that's why root of E1 phase value is 707.11 whole square plus 70.71 whole square, that is equal to 710.62 volts. This is the delta connection. This is the line voltage and phase voltage for the delta connection. Okay, thank you. This is the uh, concepts. That is the numerical problems and effect of harmonics on line EMF, total EMF, and induced EMF, and pitch factor, distribution factor, and winding factor, and some numerical problems we discussed here. And in the next class, I will discuss armature reaction in an alternator. Okay, thank you.